Okay, well, hello everybody. It's my pleasure to introduce our speaker for today. It's Erik Paemurru from the University of Miami. He will tell us about counting divisorial contractions with center a CAN singularity. Please.
Hello, everyone. It's a pleasure to have this opportunity to speak here. Yeah, and I'll talk about the classification of divisorial contractions in a special case, and both classification in terms of local analytic setting and in the algebraic setting. So first, I'll explain briefly the meaning of the words in the title. So divisorial contraction. So this is just a blow up in the Mori category, meaning the varieties have terminal singularities, Q-Gorenstein terminal singularities. We're contracting an extremal ray. We'll have an exceptional prime divisor for this contraction, and the anticanonical divisor is relatively ample. So yeah, these are the objects we'll be working with, divisorial contractions. And the second word in the title that might be new was CAN singularity. So compound AN singularity. This means it's a singularity that is a complex space germ that is given by a polynomial or power series. It's a hypersurface singularity given by a single power series locally analytically. The power series is of the form xy plus g. It should be a t here. xy plus g, where g has multiplicity n+1. And multiplicity here we mean least monomial of g has degree n+1. So for example, CA2 is xy plus z cubed plus t cubed. This is one example of a CA2 singularity, but there's infinitely many, uncountably many non-isomorphic CA2 singularities. So for example, we could also look at xy plus z cubed plus t to the 6. Okay, so we look at divisorial contractions where the center is a point, namely a point which is a compound AN singularity. And considering these such divisorial contractions, today I'll show how to simplify the existing classification, slightly simplify it. This is the main part of the talk. Next, I'll talk about the number of such divisorial contractions. After fixing a variety, we can count the number of these divisorial contractions. And finally, I'll talk about the algebraic classification. The divisorial contractions, according to the existing classification, these are weighted blowups. So what's a weighted blowup? So we start with affine space AN with coordinates x1 to xn. And we choose some positive integers, w1, wn, that for variable xi, we have the corresponding weight wi. And then we can talk about the w1 up to wn blow up of affine n space. So this means we add an extra variable u, and we look at the affine space of dimension n+1, we remove some irrelevant locus, like in the construction for projective space, we remove the locus where all of x1 up to xn are 0. And then we take a geometric quotient with a diagonal action, C star action. This is a geometric quotient. And the C star action is lambda times u x1 up to xn is lambda to the -1, lambda to the -1, u lambda to the w1 x1 up to wn xn. So we have an action, we take away a relevant ideal, and we can take the geometric quotient. And this we call the weighted blowup, or the w1 up to wn blowup of affine space. And if we have a subvariety in this affine space, we can take its strict transform and restrict this weighted blowup to this strict transform. So that's what we call the weighted blowup of this subvariety inside affine n space. Maybe I'll mention here that yeah, so this is not an intrinsic definition. We choose coordinates, embedding integers. So I'll give a slightly nicer intrinsic definition. So we can look at, instead of choosing positive integers for variables, we can look at a valuation on the function field, a divisorial valuation. This valuation defines a filtration of ideal sheaves IM generated by all functions with value at least m. And then the weighted blowup along this valuation is just the product of the direct sum of these ideal sheaves. So yeah, this is intrinsic, and it follows quickly from this definition that every divisorial valuation, every divisorial contraction is a blowup along a divisorial valuation. These, with this definition too, these are precisely the normalized blowups. Normalized blowups, yeah, where the exceptional divisor is prime. And in definition 1, these are precisely the blowups along subschemes with support a point. Okay. And the reason we talked about weighted blowups is that divisorial contractions have been classified as weighted blowups. So through years of work by Hayakawa, Kawakita, Kawakitayamamoto, we have the following result. Every three-dimensional divisorial contraction with center a point is locally analytically equivalent to a restriction of a weighted blowup of a quotient space. So this is the ambient space, and we restrict it to a codimension 2 complete intersection. So this C5 quotient by mu m here is the groups of unity, roots of unity, mth roots of unity, roots of unity. So it's a cyclic quotient singularity here. Choosing positive integers corresponding to the orbifold coordinates, we can define the weighted blowup of this cyclic quotient singularity. inside this cyclic quotient singularity, we'll have a 2-dimension-2 complete intersection. And this, we can restrict the weighted blowup of the ambient space to this codimension-2 complete intersection. And this is how the 3-dimensional divisorial contractions with center a point are classified. There is one exception that it hasn't been published yet, this result on when the point is a CDN singularity or CEN singularity, and when the discrepancy of the divisorial contraction is 1. So there's some unpublished preprint on this by Hayakawa, but yeah, but it's not been published yet. So this case, I can't say that it's done. Okay. And in this theorem, it said local analytically equivalent. So I'll say what I mean by this. So this just means that we allow local biholomorphisms around the centers of this map of this morphism and around the exceptional loci. So we allow, yeah, local biholomorphisms on the base and upstairs. So as before, we know that these weighted blowups, these depend on a lot of things. So this depends on the embedding, this depends on the coordinates we choose, and on the positive integers, W1 up to Wn that we choose. So then naturally we can ask, when are two such weighted blowups the same? And the same here, well, we could say up to isomorphism over X, or in this case, I'll look at up to local analytic equivalence. To this end, I'll define weight respecting maps. The simplest example is if we have an automorphism here, C curly braces X. This is the convergent power series. Convergent power series. In X1 up to Xn. We can look at an automorphism of this convergent power series ring. And we can say what happens with the weights. So we give positive integers weights to these variables. Say weight is Wi. This naturally defines a weighting on monomials. Weighting on monomials is if we have, for example, x1 times x2 squared. Weighting on monomials will be W1 plus 2 times W2. And then the weighting of any power series is the least weight among monomials of F. In other words, choosing these weights to the variables W1, Wi or Xi, this defines a monomial valuation on the function field. So now that we have weights for all power series, we can say that this automorphism is weight respecting if the weight of a power series doesn't change when we apply psi. The weight psi of f is equal to weight of f. So this is the simplest case if our space X is just a Cn. More generally, we have a subvariety of Cn. So we have complex spaces X and X prime inside different dimensional spaces Cn and Cm. Complex spaces X and X prime contain origins. We say that the local biholomorphic map psi from X to X prime with inverse theta is weight respecting if for every j, so the variables on Cm are yj here, if the weight of psi j is at least the weight of yj. And also for the inverse, the weight of theta I is at least the weight of xi. Now, how it's written right now is not completely rigorous because, well, we have weights for variables xi and yj. So xi and yj have weights. But it's maybe perhaps less clear how to define weights for the coordinate rings of x and x prime. So this psi j and theta I, we should choose these to be power series in Cx and Cy. And there's lots of choices for these representatives with different weights. So we say it's weight respecting if we can choose these representatives psi j and theta I such that these represent the maps psi and theta, the inverse, and these weight conditions hold. So this is a very natural condition we can put on the maps, weight respecting. The reason we define this is the following lemma, that if we have two weighted blowups, meaning we have weights for the variables xi and yj here, then these two weighted blowups are locally analytically equivalent if there exists a weight respecting map from x to x prime. I'll give a so let's say x and y have weights 4 and 3. Then we'll look at the curve inside affine space, affine 2 space. So we look at the map from x to x prime, where x is given by x squared plus 2cxy plus y squared, and x prime is x squared plus y squared. So this map diagonalizes this form, quadratic form. So we send x to x minus cy, and then we scale the variable y. But this map is not weight respecting because weight of x minus cy is equal to 3. But weight of x is equal to 4. So applying this map, we decrease the weight of some variable. So not all, when we want to diagonalize some quadratic form, not all maps will be weight respecting for this. But we can do it in a weight respecting way. Namely, we send y to minus cx plus y, and then scale the variable x. Now, the weight on this right-hand side is 3. And it's equal to the weight of y, which is 3. So we can diagonalize the quadratic form in a weight respecting manner. I'll mention also about projections. So let's say we have a variety y minus x inside A2 with variables 1 and 2, or weights 1 and 2. Then we have 2 maps from this. One is sending x, y to x. The other one is sending x, y to y. So if we choose on this A1 weight x is 1, and if we choose here weight y is 1 at 2. So what do we have? We'll have to, if when we want to decide whether it's weight respecting, we have to look at the inverse maps also. The inverse map sends x to x comma x. So this this inverse map here is not weight respecting because weight of x, the second coordinate is x, but above here we have weight y is equal to 2. So this map so this map on the left, it's not weight respecting because both the map and its inverse have to the coordinate function's weight has to be at least the weight of the coordinate. On the right-hand side, it would be weight respecting. At the moment, it's a bit strange because it's A1 and it has only one variable with weight 2. But if we added more variables, it would be easier. Okay. So we'll use these weight respecting maps to simplify the classification of divisorial contractions. Here I'll state the classification of divisorial contractions. Every divisorial contraction would center a CAN point. So it's 3 cases. The most general case is when the center is a CAN point. And then the first case is R1, R2, A1 blowup of XY plus G. And then there are some combinatorial conditions. Weight of G is R1 plus R2. And then a bunch of combinatorial conditions for R1, R2, and A. For the second case is a special case when the point is a CA1 point, not just a CA1 point, but the CA1 point of this form, xy plus z squared plus t cubed. And the blowup is 1, 5, 3, 2 blowup. The third case is when the center is a CA2 point, and we have a 4, 3, 2, 1 blowup. Here, the conditions are more difficult. So the power series F has to be of this form. So x squared plus y squared plus 2cxy plus 2xp plus 2c, well, and so on. And there's lots of conditions on this power series F. So yeah, C is any complex number except for two cases. Weight of G is at least 6. Power series P contains only monomials of weight 2 and 3. So it's not a very easy case to work with explicitly. But we can say something about this last case immediately. So we see that there are two quadratic terms, x squared plus y squared. There's a term z cubed. And from this condition that t squared is in P, so t squared is in this term. These are, in some sense, lowest order terms. Not exactly, but in some sense. So if we ignore these weights 4, 3, 2, 1 for a moment, we can diagonalize this quadratic part as shown before. Well, we can do this also in a weight respecting way, as I showed. Next, we can do this transformation x goes to x minus t squared. After this transformation, x goes to x minus t squared, we'll have x squared plus y squared plus z cubed plus t to the 4 plus some other terms. And now, with respect to weights 1 over 2, 1 over 2, 1 over 3, 1 over 4, all of these other terms are higher order. And there's a classical theorem that we can remove these higher order terms locally analytically. So the conclusion is it's a CE6 singularity of the form x squared plus y squared plus z cubed plus t to the 4. But note that these transformations we used x goes to x minus t squared. So if we look at the original weights, then x minus t squared, the weight of this is 2 because weight of t squared is 2. And this is less than the weight of x. So this coordinate change cannot be weight respecting. And in fact, there cannot be any weight respecting coordinate change to this form because the weight of this power series is 4, the least weight term is t to the 4, while the weight of f is 6, as one can check. So how did we transform it into this form? We used two statements. So this is removing these higher order terms. So the first one is if a power series defines an isolated singularity, then there exists an automorphism of the power series ring such that psi of f is the truncation of f up to degree n, meaning we can remove all higher order terms. And the corollary of this is a corollary of a slightly more precise statement related to the above, is that if the least, let's see, yeah, if the least weight non-zero part f0 of f is among the following, then there exists an automorphism psi of C of x such that psi of f is equal to the least weight part. So if the least weight part is among these normal forms of ADE singularities, also called simple singularities, then we can remove all of the higher order terms. So these are completely classical theorems, but what I did then is that I proved weight respecting versions of these. So the statements are exactly the same, except we add the words weight respecting. Weight respecting. So if f defines an isolated singularity, there exists a weight respecting automorphism that removes higher order terms. And similarly, if the least weight part is one of these normal forms, then there exists a weight respecting.
Excuse me,
Yes.
may I interrupt?
Yes.
Could you show me page 7, previous page?
Of course. Yes.
So you say that the CA2 point above is CE6 singularity. But
Yes.
what's your definition of CE6 singularity?
Right. So CE6. I made a typo. It should be a E6 singularity. Sorry. Of course. Yeah. Thank you.
CA2
So yeah.
6. Sorry,
Yeah. So
it doesn't make sense to me.
yeah. So E6 singularity is of this form.
But
Local
then,
identity.
what you mean is,
So yeah, it was a typo. It shouldn't be CE6. It should be E6.
but E6 singularity is two-dimensional.
Oh, so
CA2 point is
right.
three-dimensional.
Right. So we can also look at three-dimensional E6 singularities, which means we just add one quadratic term into the equation. At exactly the same normal form, same equation, but we add one variable and one quadratic term.
I mean, I think we are just using a different terminology.
Right, yeah. So
I mean, I thought you meant by C6 singularity which has a hyperplane of E6 singularity.
right. So here, yeah, it was a typo. It should be E6. Yeah, threefold
notion. Oh, okay.
Yeah.
Okay. It's a typo.
Threefold E6 singularity. Yeah, sorry. Yeah, threefold E6 singularity. Yeah. So these are, yeah, and in this corollary, I don't give any dimension restrictions on this n. So we can add lots of quadratic terms and extend this usual definition of Duval singularities to higher dimensions. And this is also classical. Okay. So now we define these weight respecting versions of these classical theorems from singularity theory. So now we have local analytic coordinate changes that in addition are weight respecting. So we can do this exactly the same simplification of this power series, but only using weight respecting coordinate changes. So the first theorem is our variables x, y, z, t have weights 4, 3, 2, 1. And let f be a power series that defines a threefold E6 singularity such that weight of f is 6. Then there is a weight respecting automorphism of the power series ring that takes f to this very simple form x squared plus y squared plus z cubed plus xt squared, meaning that the weighted blowups of this x squared plus y squared plus z cubed plus xt squared, the weighted blowup of this is isomorphic to the weighted blowup of this previous very complicated conditions power series. And we can do a bit more. So above, we simplified the power series to a very simple form, but we can actually remove these descriptions with power series completely. So the theorem is every three-dimensional divisorial contraction with center a CAN singularity is local analytically equivalent to either an R1, R2, A1 blowup of F, where F defines a CAN singularity, and weight of F is R1 plus R2. The combinatorial conditions on R1, R2, A are still the same, but now we have no restriction on what this F looks like, as long as its weight is R1 plus R2. Similarly, the second case is 1532 blowup, where F defines an A2 singularity, so threefold A2 singularity. I'll go back for a moment. So this xy plus z squared plus t cubed is exactly a threefold A2 singularity. And weight of f of 6. And the third case is 4321 blowup, where f defines an E6 singularity and weight of f is 6 again. So now we have description of divisorial contractions without any explicit power series, only geometrical combinatorial description. So this simplification part is now done. Okay. Next. So yeah, first I'll mention, so what does it mean to classify divisorial contractions? So in some sense, this below theorem that uses Kawakitayamamoto's and Yamamoto's result and simplifies it a bit. This theorem is, in some sense, it's a classification, but we can make it precise that a classification we can say is a description of local analytic equivalence classes of divisorial contraction. So that's, in some sense, a nice form of a classification. And this is what we've achieved with the above proposition. But the previous two ones don't show it yet, but similarly, we can show that any two of the above weighted blowups are locally analytically equivalent if the weights are the same. So this describes the local analytic equivalence classes of divisorial contractions with center a compound AN singularity. And then this, I posed the problem of finding such descriptions in other cases, describing the local analytic equivalence classes. So this would make it easier to, let's say, decide whether you're given divisorial contraction, which case does it lie in? And Okay. So once we have these local analytic equivalence classes, we can count how many of these equivalence classes we have. So we look at divisorial contractions with center a CAN point. I also added the case where the point is a smooth point. So we have three cases: smooth point, divisional contractions with discrepancy 1 with center CAN point, and the case where the CAN point admits divisorial contractions with discrepancy more than 1. So yeah, in this first case, the singularity only, we look at the case where it only admits discrepancy 1 divisorial contractions. So just looking from the table, we immediately get these following counts up to local analytic equivalence. Well, perhaps not immediately, but yeah. And this middle row, for example, this has been done before. This has been done by, let's call it Kawakita. Yeah. And these counts of divisorial contractions with least discrepancy in non-Gorenstein case, for example, was done by Hayakawa. So these are classical results. Then result for smooth points, this is also known, it's clear. So everything else here is either immediate or known for a long time. So yeah, on the rightmost column is this local analytic equivalence that we talked about. The middle column is isomorphism over the base, so algebraic classification. So what I'll mention here is this last case, how to show that if a singularity admits 1 divisorial contraction with discrepancy at least 2, then it admits uncountably many divisorial contractions with discrepancy at least 2. How do we do this? We do this by constructing an automorphism, which I call psi-c, that is not weight respecting and which fixes the power series F, this one of the local normal forms that we chose, that we had before. So this automorphism psi-c, this induces a unique map on the blown up spaces. So we can consider the blow up of X, and we can consider the blow up of X composed with this automorphism. And in general, we get 2 different blowups. There's a unique bimeromorphic map that connects these. And we can show that these psi-c, these will not lift to the blown up spaces. I'll give a specific example. We look at the general case with CIN. So our power series F here is xy plus g. We look at weights 1, R2, A1, where R2 and the discrepancy A are bigger than 1. And then we construct an automorphism that fixes F. I construct the automorphism by sending variable z to z plus cx. Since x has weight 1, z has weight 2, we see that this map decreases the weight if c is non-zero. And if we look at what just this map, sending z to z plus cx, what it does to f, it introduces some terms involving x. But we can easily get rid of those terms by a coordinate change, y goes to y plus h for some power series h. This also will not be weight respecting, or the weight here will be less than the weight of y. And we can show that this does not lift the weighted Blowup spaces. Okay, and lastly, I'll talk about the algebraic classification. So far, except for this previous uncountability example, everything was local analytic. And we found some cases where algebraically there are uncountably many divisorial contractions. So what's the next step after we have uncountably many of some objects in algebraic geometry? Well, we want to parameterize them. Or, yeah, before parameterization, the question would be, does there exist an algebraic one? So this is known if you have a local analytic description of a weighted blowup, or local analytic description of any blowup with center a point, then there exists an algebraic blowup with center a point. I mentioned, yeah. So you can extend blowups of points with possibly non-reduced structure from analytic setting to algebraic setting. Remark. Can extend blowups of points with possibly non-reduced structure from local analytic to global algebraic setting. Note that this does not hold if we blow up positive dimensional centers. It does not always hold. We can't always extend such local analytic map terms to global algebraic ones. Okay, but I'll show now how to extend it as a weighted blowup. So in a very compact description. So we start with a variety X in affine space that's given by some ideal I. And let's look at the local biholomorphism from X to some complex space Z. Let's choose positive integer weights for variables y1 up to ym. So these are variables on this ambient space of Z. That means we can define a weighted blowup of Z. So that means we'll have a weighted blowup of Z and the biholomorphism from X to Z. So what we want to do now is define some algebraic variety such that its blowup is the same as the weighted blowup of Z. We do it as follows. We define the variety X prime. So this will be given by the zero locus of the ideal I plus the ideal generated by psi1 taken up to degree w1 minus 1 minus y1, etc. up to psi m taken up to degree wm minus ym inside this affine space an plus with dimension n plus m with variables xi and yj. We see that this right x prime is isomorphic to x because we can just project away the variables y1 up to ym. So we want to describe a weighted blowup of x prime. So we choose weights for variables xi. We already have weights for variables yj. So now we have a weighted blowup of x prime. Note here that this isomorphism from x to x prime is not weight respecting. This projection here is not weight respecting. But there exists a weight respecting map from x prime to z, meaning the weighted blowups of x prime and z are local analytically equivalent. So this describes an example of an algebraic blowup that's local analytically equivalent to a given analytic blowup. The proof is very simple. So we can make a coordinate change sending yj to yj plus lower order terms of psi j minus psi j the whole power series. It's very easy to see that it's weight respecting. So this takes psi 1 psi 1 less than w1 minus y1 to y to psi 1 minus y. So after this coordinate change, local analytic coordinate change, this complex space we get is. So when we have the graph of psi, we can now project to z. And this projection to z is weight respecting. And this is the whole proof. I'll mention here that that for example, this can be used to non-toric divisorial contractions to projective three space, for example. So constructing the toric ones is very easy, but yeah, now we can construct also other ones and run the Sarkiso program with such divisorial contractions. So in this proposition, as I stated, we define one example, algebraic example of a local analytic type of a divisorial contraction. But actually, I hope or I expect that it describes all of the divisorial contractions of a given local analytic type. So I expect this proposition to be parameterizing all divisorial contractions, assuming we have a description of the local analytic type of divisorial contractions. Okay, thank you.
Thank you for a talk. Any questions, ladies and gentlemen? Let me check.
Erik, I have a question. Do you expect to use the same ideas in order to get the similar results for other compound singularities, the M, En?
Yeah, so the most natural next case would be to look at CDN and CEN singularities, but this classification is not quite completed, not published. But yeah, the ones that are published, they can be simplified exactly with these methods. I expect that they can be simplified with exactly these methods.
Okay, I see. Thank you.
Any other questions? Well, if there are no questions, so let's thank Erik again. And that was my pleasure. See you next week. Thank you very much. Bye.
Bye-bye.